In the last video, you saw how I used ChatGPT 4 to create a stand program to help predict the outcomes of Premier League matches. In that video, I basically filmed it live without ever having done it before, to truly test if ChatGPT could give me a compilable stand code without any prompt engineering or any bias from my side. And I think we could all agree that it did a pretty damn good job. It was able to generate a stand code that seemed sensible and ran out of the box the first time. The only place where it really got confused was where it initially suggested a Poisson distribution for the likelihood, but when I reminded it that it was actually a goal difference, it ended up becoming a normal distribution. But one thing I didn't do in the last video was actually explain what ChatGPT had coded. I just copied and pasted into the Jupyter notebook. And what some of you might have noticed when I did this was that the result was that Newcastle was winning about 26% of the time. Now, this might make sense, but it actually seems a little bit low given where Manchester United and Newcastle sit on the Premier League table currently. And I think this highlights a slight danger with using ChatGPT naively for coding and modeling purposes. If your goal is just to get something to work, then ChatGPT is really good. But remember, when we do Bayesian inference, a lot of the difficulty is in the choice of the process model that you end up using to model the data generating process. And a poor choice of model can have large consequences on the quality of the output that you get in the end. So in this video, I'm going to critically evaluate what ChatGPT made for us in the last video, and then also suggest some improvements that could have been done to get to a better outcome in the end. All right, so here we can see the stand code that ChatGPT made. Let me just first explain to you how this all works. So the first thing we can see is we've got 5 different types of parameters. And we've got each team's attack strength, which is a vector of length t, where t is the number of teams. Each team's defensive strength, 2 parameters which govern the distribution of attack and defense strengths, respectively. And then also a parameter which tells you about the home ground advantage. So as we can see here, these are where the priors are located. You can see the attack strength and defensive strength are normally distributed, where the variance is these different towers. And these towers are then Cauchy distributed with parameters 0 and 1. And we call this structure a hierarchical structure, where it really means that the prior here, also the parameters in the prior here have a prior themselves. So call that a hierarchical structure. We've got the home ground advantage, which is also normally distributed. Now, what's really interesting here is that the eventual goal difference is assumed to be normally distributed, where the mean is given by the sum of the home ground advantage plus the difference in attack strength of the home team minus the defensive strength of the away team. And immediately I look at this and I'm just not really sure this is the most optimal thing. Look, and at the end of the day, I do agree that the general structure of what's happening, it's quite common to model margins as the difference between abilities. So, the strengths of the different teams, and then add a home ground advantage as a kind of additional thing that the home team gets. But I don't really understand why it would have anything to do with the attack strength of the home team minus the defensive strength of the away team. Personally, I think that the attack strength and the defensive ability of the teams are somewhat independent of the fact whether they play at home or away. I feel like that's slightly different information. And so I don't quite agree with this. And the second thing is that independently trying to estimate both attack and strength and defense for each team is pretty difficult, especially when you don't have any feedback that's coming into the model. So it's not as if we observe anything to do with the absolute values of how much each team scored or how much each team defended. We're simply estimating we're simply passing into the model what the goal difference is. So for me, I think this is a little bit of an over parameterization. So what I think actually makes much more sense here is to have a single vector of length t, which is just the team strength or team ability, and replace this expression here with simply the difference in team ability between the home team and the away team. That's going to do 2 things. That's going to firstly, drastically cut down the number of parameters. So it's going to lead to a better fit. And I also think it's going to lead to less overfitting as well, because there's less parameters. So that's the first thing I would do. Now, the second thing that I noticed was ChatGPT decided to not estimate the variance in this normal distribution, and instead it just made it 1. And for me, I'm just not really sure why it would do that. The whole reason why you do Bayesian inference in the first place is to be able to estimate things like variances super robustly and with basically principled regularization. And so what I would have thought would be better is to define another parameter, sigma, for example, slap a prior on it into here and have the model estimate what sigma is rather than just say that it's 1. Now, the third gripe that I have with this model, and it's not that it's wrong, it's just that it's decided to model the goal difference as a normal distribution. And we know that goal differences are integers, they're not continuous, so a normal distribution isn't really a great representation of reality in this instance. And I'm not saying that a normal distribution is a bad choice. It's actually quite a good choice because it's very simple, it's widely used in a lot of statistics, so a normal distribution is fine, but I just think that when modeling football matches, and and you're modeling the goal difference of football matches, and you know that they're integers, it definitely does make sense to try and use a more appropriate probability distribution to model that. What's really common is called a Skellam distribution. So you can read about Skellam distributions here. Essentially, they're constructed from the difference between two Poisson processes, and they look almost very similar to a normal distribution. They have quite similar properties, except for the fact that their support is only on sort of the range of integers, including negative integers as well. So I think what I would have done here is probably used a Skellam distribution, and that's maybe that's a little bit difficult because in Stan there isn't any Skellam distribution natively. You have to construct that with a custom function. But it's certainly possible, and I think building a custom function in this case would be really advantageous because it would probably lead to much better results. And so that's probably the 3 things that I see, with this code that could be improved. And when we scroll down to the results, we can see what the results are. As I mentioned before, the results for the away team winning 26%, results for Manchester United in this case winning. So away team in this case was Newcastle. Manchester United in this case was the home team, 37%. Maybe that seems slightly off given the relative positions of where Newcastle and Manchester are currently. And so what I've managed to do here is create an alternative model that's based on the code that ChatGPT provided, but I've implemented a couple of the suggestions that I talked about before. So the first one is that I've reduced the number of parameters. So instead of having sort of attack strength and defensive strength, I just have a single vector here called team strength. And in the likelihood statement here, you can see that I've got the home ground advantage plus the difference in team strengths, or the home ground advantage plus the team strength of the home team and the team strength of the away team. Now, there's not a difference here. I'll get to that in a second. But just know what I'm doing here is I'm not estimating simultaneously attack and defense. I'm just making it about team strength now. And the second thing you'll notice is that I've changed the likelihood distribution to be a Skellam. And so this is, like I mentioned before, you need to create your own Skellam function because this doesn't come out of the box in Stan. But essentially what I did was I just created a function here, ripped straight from the definition of what a Skellam is. So that's essentially what this equation is. This is what this function does. And then, using Stan's target plus equals notation, I've got a video on that. I've managed to add its log probability mass function to the posterior in this manner. Now, what's really interesting about a Skellam function is that it takes in as inputs the team strength of the home team and the team strength of the away team as lambda 1 and lambda 2. So what I've done here is rather take the difference between the two. What I've done here instead is said, well, the home team's strength is its team strength plus some home ground advantage, which we're going to estimate. And the second, lambda 2, is just the away team's strength. And that's it. So we don't need to specify the difference here. And the other thing you notice about a Skellam distribution is that it doesn't actually take in anything to do with the variance. So it's quite, because it's constructed out of a difference between Poisson distributions, you don't need that kind of variance parameter. And so there's no analog to sort of this one here, which is ChatGPT's attempt at modeling the variance. There's no analog to that, so we don't need to have that in there, and so there's no parameter. So again, that cuts down the number of parameters we need to estimate. The other thing that's really important to note about a Skellam is that these two team strengths, here and here, they need to be greater than 0. And so what I've done is I've put constraints on the parameters. Team strength has to be greater than 0, and also home ground advantage is also greater than 0. So it sort of acts like another layer of regularization that's going to help us get a fit. Now let's run this code. So I'm going to run this code exactly the same way as I ran the GPT code. So let's do that. Okay, so now it's finished. Let's check the results. We can have a look at the results here. And we can see now that the probabilities of the home and away team winning are quite different. So the draw probability is 20%. The away team winning, which is Newcastle in this case, now has jumped up to 42%. It was before 26%. The home probability winning is roughly the same at around 37%. So, and you notice that that's quite different from what we had before. So which one is right? How can we choose which model? And one way we can do this is to evaluate the model using what's called the Pareto smoothed importance sampling leave one out cross-validation method. It's a really long thing to say, but essentially what this is it's a statistical method to try and estimate what the accuracy of a leave one out cross-validation sampling would be for Bayesian models. And you can find this in the RViz package. So let's now do that now. And RViz also has a really nice function called compare, which allows us to compare the results of the leave one out cross-validation. You can see here that if we compare the results of GPT and the alternative, we can see that the alternative model has a much lower deviance. It's about 20% lower. And just so you know, the deviance is basically an estimate of the out of sample error. So basically from these metrics, it's probably best to go with the alternative model, because the alternative model, the model using the sort of suggestions that I had before, really does have a much better sort of out of sample fit. So what's the moral of the story here? Is it just that ChatGPT is no good at doing Bayesian inference? Well, not at all. ChatGPT is an invaluable resource to use to help you with your modeling. I'm sure that with a bit of better prompt engineering and getting it to ask to explain itself, it could have done a better job. But one thing that I think this example highlights that's really important is to not take results just at their face value, especially when you're doing Bayesian inference. It's really important to know how to read stand code and to know what you're doing when you're doing Bayesian inference, so you can spot where ChatGPT could improve. So ChatGPT is an amazing resource, but it's really important that you know your basics so you can effectively scrutinize and enhance its suggestions. So if you're looking to get started with Bayesian inference, I have a short YouTube series on my channel called Bayesian Inference and Stan. It's aimed at beginners and should give you everything that you need in order to get started with Stan and Bayesian inference. Make sure to comment if you have any questions or suggestions, give the video a thumbs up, and subscribe to the channel and turn your notifications bell on in order to stay up to date with the latest content on Bayesian inference. See you in the next one.